What if the most universal trait of an intelligent civilization is its ability to destabilize its own planet? And what if the only trace such a life leaves behind, light years away, is the damage it caused? Imagine millions of years ago, dinosaurs driving cars through cities made of mile-high towers. An absurd vision. Yet over tens of millions of years, all direct evidence of such a civilization, its cities, its machines, could turn to dust. We've been searching for alien civilizations for half a century. But what if the only one we've missed is the one that lived here before us? What if our civilization is just another layer waiting to be buried? A thin film in the rock, indistinguishable from stone, hinting that we may not have been the first advanced beings to walk this planet. How could we ever know a civilization existed before humanity if every trace of it was erased? In this journey, we'll dive into a bold scientific experiment born inside NASA and the Planetary Science Institute, the Silurian Hypothesis. It adds a provocative question. Could an industrial civilization have arisen on Earth long before humans? And if so, what traces would it have left behind? This study will take us from Earth's ancient climate catastrophes to futuristic astrobiology, showing how the search for an incredible past is reshaping our understanding of life on Earth and beyond. Earth is more than 4.5 billion years old. Complex life has thrived for hundreds of millions of years. Meanwhile, Homo sapiens have existed for only about 300,000 years, a blink in geological time. If we compressed Earth's history into a single year, modern humans would appear only in the final few minutes before midnight on December 31st. Could another intelligent species have evolved and built a civilization in some distant month of that calendar, long before us? It sounds like science fiction, and indeed the Silurian Hypothesis takes its name from science fiction. It's inspired by a 1970 episode of Doctor Who, where intelligent reptilians from the Silurian period awaken in the present day. In reality, the Silurian period, around 430 million years ago, predates large land animals, meaning any ancient civilization would have had to arise much later. But the name hints at the provocative nature of the question. If not humans, then who? Could some species of dinosaur or early mammal, at least theoretically, have achieved intelligence in industry many ages ago? Geology teaches us humility when it comes to preservation. The fraction of life that ever fossilizes is vanishingly small. Out of the billions of dinosaurs that lived on Earth for 180 million years, we have only a few thousand nearly complete fossils, roughly one fossil for every 10,000 years of their existence. Entire species can appear and disappear, leaving almost no trace behind. A short-lived industrial species like humanity might not appear in the fossil record at all. But what about our cities and artifacts, you might ask? Plate tectonics tirelessly recycles Earth's crust. The oldest exposed land surface still visible today is only about 1.8 million years old. Over a few million years, wind, rain, and the planet's own shifting crust erase or bury almost everything. The ocean floor sinks and renews itself. No seabed older than 170 million years exists today. In short, any direct evidence of a civilization older than a few million years would be unlikely to survive in its original place. If New York City had been built 100 million years ago, we would likely find nothing of its skyscrapers. They would have crumbled, been subducted into Earth's mantle, or scattered into dust. Knowing this, scientists developed the Silurian Hypothesis, not to claim that such a civilization ever existed, but to ask a deeper question. How would we even know if it had? Our modern global civilization is rapidly imprinting itself on Earth. But what will remain of us in 100 million years? NASA climatologist Gavin Smith and astrophysicist Adam Frank realized that to answer this question, we must catalog the geological fingerprints of the Anthropocene, the epoch of pervasive human impact. These fingerprints are forming right now in our air, water, soil, and through them, future geologists or perhaps extraterrestrial xenoarchaeologists will know that we once existed. Some clues are straightforward. First, carbon spikes from fossil fuel combustion. By burning coal, oil, and gas, we release ancient carbon into the atmosphere, creating a distinct imbalance in the isotopic ratio of carbon. This isotopic shift, the depletion of carbon-13, known as the Seuss effect, will be recorded in sediments across the world. Second, climate warming and ocean chemistry. The greenhouse gases we emit heat the planet. Future rocks will record a sharp global temperature spike and evidence of ocean acidification and deoxygenization. For example, our use of nitrogen fertilizers disrupts the nitrogen cycle, and this change will appear as an abnormal isotope ratio of nitrogen in sedimentary layers. Third, synthetic materials and pollutants. Plastics and artificial chemicals, they're already accumulating in sediments. Tiny plastic fragments are settling to the seafloor, forming a detectable layer that could persist through geological time. Likewise, synthetic molecules, from steroids to persistent organic pollutants, are new markers that could remain preserved in rock. Furthermore, there are heavy metals and rare elements. Industrial society has dispersed unusual concentrations of lead, chromium, and rare earth elements far and wide. Future strata may show abnormal spikes of these metals corresponding to the Industrial Revolution and beyond. Nuclear activity has also left unmistakable radionuclide traces in recent sediments. Some of those isotopes have long half-lives, serving as a precise timestamp of the mid-20th century nuclear era. Here, carbon-14 deserves special mention. It forms when a fast neutron collides with atmospheric nitrogen-14, briefly creating excited nitrogen-15, which ejects a proton and becomes radiocarbon. That carbon-14 then binds with oxygen to form CO2, entering plants, animals, and humans. Above-ground nuclear tests in the 50s and early 60s released a massive surge of neutrons into the atmosphere, doubling global carbon-14 levels in less than a decade and leaving a distinct worldwide bomb pulse. The spike spread around the planet, creating a timestamp now used to date ivory, paintings, wine, and even human remains. As fossil fuel CO2, which lacks carbon-14, fills the air, it dilutes that signal back toward pre-bomb levels, leaving yet another distinct Anthropocene marker directly tied to industrial activity. Each of these signals is deposited globally in ice cores, ocean mud, and lake sediments. The imprint of our civilization resembles less a buried city and more of a geochemical ring in a tree trunk. As Adam Frank notes, by the early 21st century, humanity had spread its artifacts and effluents from the ocean depths to the upper atmosphere, even reaching the moon. Future scientists won't need to stumble upon a fossilized smartphone to know we were here. They'll see it in the chemistry of rocks worldwide. But this raises a profound counter-question. If these are the markers of any industrial civilization, could we find such markers buried deep in Earth's ancient past? If industrialization once occurred in another species long ago, the best evidence might be faint chemical fingerprints scattered across the planet. We know what to look for. So, where are those signals? To search for such traces, scientists today turn to Earth's most dramatic climate upheavals. Do ancient layers show multi-proxy patterns resembling an industrial fingerprint? Rapid carbon excursions, warming, acidification or anoxia, and spikes in metal concentrations on a global scale? One such event stands out: the Paleocene Eocene Thermal Maximum, or PETM, 56 million years ago. The PETM was a mysterious fever in Earth's history. With a geologically brief interval, global average temperatures rose by at least 9 to 15 degrees Fahrenheit. In a world with almost no ice, subtropical forests thrived near the poles, and the Arctic Ocean warmed to around 70 degrees Fahrenheit. Crucially, the isotopic record from PETM sediments show a massive release of light carbon, carbon-12, into the atmosphere. The ratio of carbon-13 to carbon-12 dropped sharply, just as it is now in the Anthropocene due to the fossil fuel combustion. It's as if 56 million years ago, nature recorded a carbon pulse strikingly similar to the one our industry produces today. And the PETM wasn't a lone anomaly. A few million years later came other deviations, mysterious warming spikes known as the Eocene layers of mysterious origin, marked by temperature surges and carbon cycle disruptions. Looking even further back, we find other strange chapters in Earth's story. Cretaceous oceanic anoxic events about 90 million years ago, when vast ocean regions lost oxygen, or even the Permian extinction 252 million years ago, which brought a sharp carbon isotope drop-off and global die-off. These episodes left chemical bands in rock layers that resemble what an industrial age might produce: an influx of carbon, rising heat, and destabilized ecosystems. Could any of these be the fingerprints of an earlier technological species? What if the PETM sudden carbon surge was the death cry of a long-lost civilization that overheated its world? It would be the plot twist of the ages. However, scientists approach this idea with caution and skepticism. They note key differences. The PETM's carbon release, though rapid geologically, unfolded over tens of thousands of years, likely too slow to reflect just a few centuries of industrial fuel burning. Moreover, there are natural explanations: massive volcanism, burning carbon-rich deposits, melting methane hydrates, or other planetary feedbacks could have triggered the warming. By contrast, the Anthropocene spike is occurring over mere centuries, an instant by geological standards. If a prior civilization's surge were just as brief, the geological record could smear it into a faint blur, nearly indistinguishable from background noise. Sedimentary layers take time to accumulate. Bioturbation, animals churning the soil, and chemical diffusion can stretch short events into broader layers. That means a rapid industrial phase might survive only as a subtle gray smudge in the strata. Easy to overlook unless you know exactly what to look for. Now imagine for a moment a world much like Earth, orbiting a distant star, a world where intelligent beings have entered their own industrial age and transformed their planet's climate. Climate change and ecological disruption might be a universal challenge for any energy-intensive civilization that emerges wherever technological life arises. In other words, the Anthropocene could have analogs on alien worlds, an alien Anthropocene. As Dr. Adam Frank puts it directly, the problem of a civilization altering its own climate is likely to haunt every technological society in the universe. If that's true, then the fingerprints of industry and collapse might already be etched in the skies of other worlds, waiting for us to discover them. Let's explore this provocative idea: how the ecological crisis on Earth might represent a universal stage in the evolution of advanced civilizations, and how this concept could guide our search for extraterrestrial life. The idea of the alien Anthropocene stems from a simple realization: it's quite possible that Earth is not the first planet ever transformed by intelligent life. Astrobiology encourages us to zoom out, to see our situation as one among many possible examples. Our own story, rapid population growth, industrialization, climate change, it could be a template for what happens on inhabited worlds across the cosmos. As early as 2018, NASA hosted the Technosignatures Workshop, which highlighted this new perspective. Scientists begin to seriously ask how technological civilizations and their planets co-evolve over time. And suddenly, ideas once on the fringes became serious questions of study. Could we detect atmospheric pollution from a distant industrial society? Might we observe colossal megastructures orbiting other stars? And how does a planet's climate respond when intelligence itself becomes part of the equation? These questions inspired researchers to create new models and search strategies that treat our Anthropocene as just one case in a cosmic experiment. Adam Frank and his colleagues were pioneers of this astrobiological approach. Their idea was that any young civilization, wherever it arises, will inevitably extract energy and resources on massive scales, and the laws of physics dictate that doing so must alter the planet's environment. As Frank explains, driving climate change may be something generic to all industrial civilizations. He argues that we must start thinking like a planet, viewing humanity's current challenges within a cosmic frame. By studying other worlds, real or hypothetical, we can begin to understand what the rules or likely outcomes might be for civilizations like our own. To explore these ideas, Frank's team developed mathematical models simulating the coevolution of a civilization and its planet's climate. They treated an alien civilization, or our own, as a global energy harvesting force and asked, what happens to population and planetary conditions as resource use increases? The results were striking. Models based on thermodynamic limits rather than Earth-specific factors produced several distinct outcomes, possible trajectories that any civilized world might follow. The first case is die-off. Here, a civilization expands rapidly and exhausts its resources, leading to deteriorating planetary conditions, for example, rising temperature. Population overshoots the planet's carrying capacity, followed by a sharp decline, a collapse to a fraction of its peak. In this scenario, remnants of the population survive in a degraded world, but a complex, high-tech society may not endure the chaos of losing, say, 7 out of 10 people. The second case is sustainability. In this path, the civilization adapts wisely over time. Population and planetary impact grow, but eventually stabilize at a sustainable, livable level. This outcome occurs when society recognizes its damage early and shifts from highly efficient energy sources, like fossil fuels, to renewables, such as solar power, before it's too late. In the models, this is the best-case scenario, a civilization achieving long-term equilibrium with its planet's carrying capacity. The worst-case scenario is collapse. Here, population and pollution rise unchecked until environmental stress triggers a sudden catastrophic breakdown. Uncontrolled energy use, renewable or not, can lead to collapse within as little as 1,000 years. Population drops to nearly zero, along with the planet's habitability. In essence, the civilization falls off a cliff, a fate that could mean extinction or a return to pre-industrial conditions. And finally, there's collapse despite change, perhaps the most troubling case. It envisions a civilization that tries to adjust, to shift towards sustainable practices, but they act too late. Initial damage triggers irreversible climate feedback, leading to collapse even after reforms. As Frank notes, you can make all the right choices and still have things not work out if critical tipping points have already been passed. These trajectories are more than theory. They form a framework for thinking about the great filter, the cosmic sieve that may eliminate most civilizations. Of the 4 paths, only one represents a truly successful, long-lived society. The others end in mass loss or extinction. The models offer both hope and warning. While sustainable futures are possible, many paths lead to a catastrophe despite technological progress. The team even drew lessons from Earth's history to ground these models, For instance, they cited Easter Island as a microcosm of overuse and collapse. This isolated human society overexploited its resources, leading to a dramatic population decline in the 18th century, a real-world extinction scenario. On a planetary scale, the message is clear. Civilizations and their planets evolved together, bound by cause and effect. If a civilization grows too fast and destabilizes its environment, the environment strikes back, shrinking the civilization in turn. As Frank and his colleagues write, our struggle to build a sustainable civilization may not be the first time in cosmic history this has happened. If we ever find evidence of such outcomes or distant worlds, it wouldn't just answer the question of whether we're alone, it would tell us how difficult survival truly is during the critical transition we now face. But how would we recognize an alien Anthropocene when we saw it? The traditional Search for Extraterrestrial Intelligence, or SETI program, listens for intentional signals, radio transmissions, or laser pulses aimed across the stars. However, the study of technosignatures expands the search to passive clues, unintentional evidence of technology or industry that could be observed from afar. In recent years, scientists have assembled an entire catalog of potential technosignatures. Among these technosignatures, the greatest progress has come from the search for industrial atmospheric gases. Astronomers are taking advantage of the exoplanet revolution. We now know of more than 5,000 exoplanets, and for some, we can study their atmospheres by analyzing starlight passing through them during transits. The James Webb Space Telescope that launched in 2021 can detect molecules such as water vapor, carbon dioxide, methane, and others on planets tens of light years away. Most of this work has focused on biosignatures, signs of life such as oxygen or methane appearing in combinations that suggest biology. But astrobiologists are increasingly fascinated by possible technosignatures in these same spectra. It sounds like science fiction. Could we detect an alien civilization by its air pollution? Back in 2014, a Harvard-Smithsonian team proposed exactly that. They calculated that a space telescope like JWST, under the right conditions, could detect the spectral fingerprints of certain CFC gases, chlorofluorocarbons, that are in an exoplanet's atmosphere. CFCs are synthetic compounds once widely used on Earth in refrigerators and aerosols, entirely artificial molecules with no known natural source. The researchers noted an eerie possibility. If you detected only long-lived CFCs but none of the short-lived ones, it might mean you were witnessing the lingering pollution of a vanished civilization. Short-lived pollutants would have decayed within a decade or so, implying no ongoing emission. In other words, astronomers might detect the ghost of a dead civilization, a world whose factories fell silent tens of thousands of years ago, leaving behind a chemical tombstone of ozone-depleting gases. Based on these ideas, in 2021, a NASA team led by Dr. Ravi Kaparapu published a study examining nitrogen dioxide as a technosignature. NO2 is a reddish-brown gas produced largely by the burning of fossil fuels. Think car exhaust and power plant emissions. It also has natural sources, but on Earth, 76% of NO2 originates from industrial activity. Kaparapu's team asked if an Earth-like planet hosted a civilization producing similar levels of NO2, could we detect it, say 30 light years away? The results were encouraging, though challenging. Using atmospheric chemistry simulations and mock telescope observations, they found that a next-generation observatory, perhaps a 50-foot space telescope operating in visible wavelengths, could indeed discern NO2's spectral signature after about 400 hours of observation. Now that's a long exposure, but not impossible. The Hubble Space Telescope's ultra-deep field took around 280 hours. Interestingly, the team noted that cooler stars, orange K-dwarfs and red M-dwarfs, would help detection, since their weaker ultraviolet light allows NO2 to accumulate longer before breaking down. Of course, the key question is, how can we distinguish an industrial signal from a natural one? The NASA study emphasizes that detecting NO2 or any gas is not by itself conclusive. Scientists must model the planet to estimate the maximum plausible natural output from volcanoes and other sources, then check whether the observed amount exceeds that baseline. If it does, and especially if the gas appears alongside other technological indicators, it could form a compelling technosignature. Notably, CFCs remain a particularly attractive target. As one co-author remarked, they are an obvious technosignature, since no known biology produces them at all. The catch is that CFCs might be rare. After all, aliens may not invent the same chemicals that we did. NO2, on the other hand, arises from any combustion-based industry, making it potentially more universal. Beyond gases, other atmospheric indicators could include unusual thermal profiles. For example, a greenhouse-warm planet in an energy imbalance, or aerosol dust and smog particles with distinct spectral effects. As a thought experiment, if aliens pointed a telescope at Earth today, they would see unmistakable signs of an ongoing Anthropocene. CO2 levels around 420 ppm and rising, deforestation altering surface albedo, and faint traces of artificial substances like CFC-11 or nitrous oxide from agriculture. They might conclude that in the 21st century something strange was happening here, either a thriving industrial civilization or a planet in peril. Our task is to reverse the roles, to study distant worlds for similar anomalies. Right now, teams of astronomers are preparing the tools for this cosmic climate forensics. Upcoming missions and concepts like the LUVOIR telescope and ESA's Ariel mission will specialize in analyzing planetary atmospheres. Meanwhile, the very same NASA 2018 Technosignature workshop sparked new funding streams for searching archival data for signs of advanced technologies. Researchers are now hunting for everything, from excess infrared radiation, the waste heat of possible megastructures, to anomalous stellar light curves that could hint at artificial objects in orbit. But what would it mean if we actually discovered evidence of an alien Anthropocene? Finding an industrial exoplanet, even one faintly scented with unnatural gases, would be a profound event. It would confirm not only that we're not alone, but that somewhere else another civilization faced the same struggles of growth and sustainability. Suppose we detected an Earth-sized planet with an atmosphere rich in CFCs and NO2. We'd know that around some distant sun, perhaps 10,000 years ago, a civilization reached a high level of technology. Did they survive their climate crisis or succumb to it? The answer might lie in the details. If short-lived pollutants have vanished but long-lived ones remain, it suggests their factories have been silent for ages. In essence, we would be reading the aftermath of catastrophe, a cautionary tale etched in the air. But conversely, if we found a planet with moderate stable levels of industrial gases and balanced climate, it could indicate a sustainable, long-lived civilization that successfully navigated its dangerous transition and achieved equilibrium. That would be an inspiring beacon of hope, showing that the great filter of climate self-destruction can be overcome. Even a null result, no technosignatures after years of searching, would still carry meaning. It might imply that technological civilizations are exceedingly rare or that they tend to be short-lived. The famous Fermi paradox asks, where is everybody? Perhaps one answer is that many civilizations burn out after only a few centuries of intensive energy use. If we observe thousands of planets with promising biospheres but no signs of industry, we may conclude that the leap from microbial life to a stable technological society is exceptionally hard to sustain. In that sense, the silence of the stars itself may be a warning. a universe littered with the remains of civilizations that fail the test of sustainability. On a more optimistic note, the pursuit of alien Anthropocenes is already benefiting us by expanding our scientific horizons. By framing climate change as an astrobiological problem, not just a local disaster, scientists gain powerful new tools to understand Earth. Comparative planetology, the study of Venus, Mars, and exoplanets, has already deepened our knowledge of atmospheric chemistry and runaway greenhouse effects. As Adam Frank notes, insights from other worlds often illuminate our own. The concept of nuclear winter was first discovered through climate models originally designed to simulate Martian dust storms. Likewise, attempts to predict the climate of an alien civilization forces us to refine our models of oceans, clouds, and planetary feedback loops. In short, looking outward helps us think inward. It's like a doctor studying many patients to better treat one. By examining the potential fates of other sick planets, we can more wisely diagnose the condition of our own. Somewhere out there, the atmosphere of a distant world may glow with the byproducts of a thriving, wise civilization, or the ashes of one that burned too bright, too fast. For now, Earth remains the only known protagonist in this cosmic story, but perhaps not the only one in history. As we continue scanning the skies for faint technosignatures and decoding the lessons of other worlds, we join a race to apply that knowledge here at home. Will humanity become a long-lived cosmic species, leaving only a gentle mark on its world? Or will our Anthropocene mark the beginning of the end, as it perhaps did for others before us? The choice is ours.